All right, finally the practice part. Okay, so we're going to run the code in R, and all the code have already been provided to the course website. Let me just share my screen. Okay. So on the Moodle website, you will see all these R code that I have here in my folder. And also these two data set for part 1. And for this R code, it actually include growth curve models for missing data analysis with CAR and MAR, and also a growth curve model for NAR missing data, so missing not at random data, so where I incorporate a selection structure of it. And also I have the code for robust growth curve model using T distributions, and also have the growth curve model with proportion outcomes, but this one is not really R code because all the R code has been uploaded to the GitHub site, and I provide the GitHub site here, and the paper is already published, so you can just try those code. And also we have the models for 1 class growth mixture model, 2 class growth mixture model without constraints, and 2 class growth mixture model with constraints to set all the variances and covariances across different latent classes to be equal. I'm not sure if we have enough time to run all these, but they are just available to you, and you can run even without, like, after this workshop. So first, let's start with growth curve model with missing data. So R code part 1, GCM, missing data analysis. So this is not NAR yet. I click that open in RStudio. All right. So first of all, we can read in the data into R, and you can just set your working directory in your part. And I save the data set in this folder, and I run this. And then I can just read the data into R. So after I read that, it actually showed me that this data set have 434 observations with 4 variables. So basically that's the National Longitudinal Survey of Youth math data. It includes the 434 students. Their math scores from the 7th grade, from the 10th grade were recorded. So it's 4 variables, 7th, 8th, 9s, and 10s. That's the math scores. Okay, and we do some export analysis. We check the data and see what the data look like, and we can calculate the means and standard deviations at each grade. Then in that case, we can just do data or the mean of math scores at grade 7 and mean of math grade at 8. But when you look at the values, it actually looks quite weird because the math scores at grade 7 is 5, and the math scores at grade, or the mean math score at grade 8 is 102, which doesn't seem to make sense. So let's look at the data. We can actually look at the data and we see that, oh, there are many 999s here. So actually those 999s just represent missing data. And just because of those 999s exist in grade 8, it caused the mean of grade 8 really large. So by just looking at that, we just try to understand more about the data. So we want to replace those 999s by NAs in R. So those are missing values. And we run this. And after that, we check our data. Then those 999s were now all NAs. okay, missing values. So we have this data set with 434 rows and 4 columns. Okay. We can attach our data so that the column names are attached. And then after attaching the data, we can just do mean of grade 7, mean of grade 8, instead of having to set data $sign, grade 7, 8. Okay, so we can now check the means. Ooh, then we have NAs just because there are missing values in it. So if you check the function of, whoops, the mean function. Okay, so then you see that there is an argument that says that na.rm, na.remove equals false. So in that case, all the missing values are included in the calculation. So it gives you the NAs. Basically, grade 7 doesn't have missing values. Grade 8, 9, 10, they all have missing values. Okay. So what we need to do is we just said na.remove equals true. And now we can actually get the average math scores at different grade. And similarly, we can calculate the standard deviations of it. And if you are lazy, just like me, I would like to use the apply function. So apply actually works on the data for each column. 2 means column, 1 means each row. So for each column, I'm calculating the mean and removing all those NAs. So in that case, I get all the means calculated for each grade by using this one line instead of multiple lines. And also I can calculate the standard deviations. And we can also find out the missing rate at each grade. So we used ace.na for each grade. That actually gave us how many NAs are there for each grade. And we get the sum of them, divide by the total sample size. That gave us a missing rate. So for the 7th grade, there's no missing values. For the 8th grade, there are 9.67% missing values. For the grade 9 is 20%. And for grade 10, it's like almost 35%. Okay. And also we can just write a function like missing rate to calculate the missing rate. So that also gives us the same thing. And for longitudinal data, we can draw the trajectory plot by using the matplot function. So the x-axis is from 7 to 10, 7th grade to the 10th grade. And the y-axis are just the math scores, but we have to take the transpose of it just to match the dimension of it. Because currently it's 434 times 4, and now for the trajectory plot, we actually just want to transpose the data matrix. Okay. And the type is line, color is black. We set the label for the y-axis as the math scores, and label for the x-axis is the grade. And this AXP argument is just tells us I'm actually setting the label of x-axis is from 7 to 10 with 3 equal intervals. That will actually make the labels for the x-axis to be exactly 7, 8, 9, 10. Otherwise, it could be anywhere like maybe 6.5, 7.5, or something like that, or maybe just 6, 7, 8, 8.5 or 10. It's just use the convenient labels for the x-axis. Okay, and after we have these trajectory plot, we can add an average or the overall trajectory to it by adding a lines where we take the means for each of the grade. Okay, LWD3 just make the line thicker, and we use a red color. So you can see like there is an increase from grade 7 to grade 10. Okay, and like I said, there are missing values. So now we use JAX to fit growth curve models to the data. To use JAX, we have to install JAX first. So it's not enough just to do a library RJAX or to install RJAX. In addition to that, we have to install the JAX software. Okay, so in the prep file I provided to you, there is an instruction like how we install R, how we install RStudio, and how we install JAX, and then how we install RJAX. So after all that R and JAX were installed, then in R, you can just install this RJAX package by using the install.packages function, okay? So since I already installed it, then I can just run the library, and then I can just run my model string. So for the first, I've specified a linear growth curve model where I specify my models here. So this is a model string where I have the likelihood function specified and the priors specified, and also the parameter reorganization or just transform some of the parameters. Okay, so I can just run these. And this is just saved as a model string. And I would definitely recommend to write this into a text form or text file. So you can use this red lines and write this model string into a model.txt function. So if you do that, it's actually saved into this folder. So basically the models are saved into this txt format. You don't actually always have to use that, because we can actually just read the inline or these text directly into JAX in R. But I always just do this because it helps me to check my code just from the text file. Okay, and then after that, I set my initial values, which is a list. So we have initial values for average intercept, initial values for average slope, and initial values for the level 1 residual variance, and also the initial values for the covariance matrix for the second level of the model. So it includes intercept, variance of latent intercept is 1, variance of the latent slope is also 1, the covariance between intercept and slope. So these are just the initial values, okay? And after that, I actually set the random number generator. So I use this random number generator and set the seed for the random number generator. If you don't set that, you still get the results. But if you repeatedly do that, you probably will get slightly different results because the random number generated in this procedure will be different. So definitely include the seed to make sure your analysis will always give you the same results, can be replicable. Okay. And after initial value is specified, we prepare our data. This is the JAX data. So in this part, if you go back to the model, we only have this Y as our data, and also this N is unknown. So we can also specify this N here. Otherwise, if in the data part, you don't include it, N equals 434, you can just change this N in the model part to be 434. So it's no longer anything like we need to let the software know later. Okay, so we can just run these 2 lines. And after we prepare our data, or set the initial values for the model, we can just run JAX. We compile our model. So this is basically just put the model data, initial values together. And the number of chance here, I use just 1, okay? And then I update my model for 8,000 times. This is the burning period. So at this point, I'm not saving any of the iteration results. But then after the burning period, so after the initial iterations were thrown away, then I try to keep the samples. Okay, so in this part, I use a CODA samples function in JAX, where we put the models here, and then I just let JAX know which model parameters that I want to monitor. So here I want to monitor the BL, BS, E2, which is the variance of the level 1 residue, and also variance of intercept, variance of slope, covariance between intercept and slope, and correlation between intercept and slope. So those are just the model parameters we have in the model. And later you will see that we can actually organize all those parameters into a vector. Like I can have my parameter 1 to be BL, parameter 2 to be BS, parameter 3 to be this. So there are just different ways or options that you can organize your results. And this way, it just, the good part of listing all the parameters, like when you see your results later, like in a few seconds, you actually know that which parameter is which, okay? Because you have the name of it. And again, we set the number of iterations to be 8,000. So we'll go into save all the 8,000 iterations. And in this part, I actually have 2 additional lines here where I keep the initial time and then the time after I run these, just to know how much time is needed to run these Bayesian analysis. For this case, I only need like 3.9 seconds, which is pretty fast, right? And depending on different laptops. So, okay, and then we can run this. Oh, after we run this, we save the model samples as a MCMC object. Okay, and once it's saved, then we can really just get the model results. So we can plot the model results, which gives us the histograms, history plots, sorry, not histogram, history plots and the density curves for each posterior distributions. Okay, how do I get out of here? Okay. And then I need to get back to my studio. Okay, so here we go. And then, this is just for 4 parameter. Remember, we have 6 parameters in total. So we have all these, or 7 actually, because we also have the correlation between intercept and slope. So 1, 2, 3, 4, 5, 6, 7. Okay. And once we plot that, and based on these history plot, we can actually see the chain actually converged, because the history plot really show a converged pattern. But in addition to that, we can actually conduct a GWAC test. GWAC test is to compare the first 50% of the chain with the last 10% of the chain to see if they have the same mean. So basically, the GWAC statistic is just a z-score. Okay, so if the z-score is between -1.96 and +1.96, it means that the chain converged. So we have the Markov chain for each of the 6 parameters, and we see that they are all between -1.96 and +1.96, indicating that they all converged. Since they all converged, we can just get their summary results. So by using the summary model results, we can get the summary results. It gives us number of iterations and the thinning intervals. We didn't talk about the thinning, but it's basically just a basic thing, like whether you want to thin the chains. And we only have 1 chain here. And this results, we have all the 7 parameters. We have their means, standard deviations, and Markov standard error, and Markov standard errors and quantiles for each variable. So we have the medians and all these 2.5% and 97.5% quantiles. Okay. And this will actually give us a 95% equal tail credible intervals. In order to get the HPD credible intervals, we can actually use the HPD interval function that gave us the HPD credible intervals for each of the parameters. Okay, so like I said, if we actually write out the parameters here, then we actually in the summary table, we know these are the parameters, we directly know which one corresponds to which. So it's just easy to see. But another way is like we can organize the parameters here, like by saving them into a vector of parameters. And here we only have a PAR, and this way we will have PAR1, PAR2, but you have to figure out which parameter is which real parameters in the model. Okay, so that's for the model estimation. And in order to calculate DIC using JAX, we have to specify 2 chains, because like I said earlier, Plummer actually defined a corrected DIC value with 2 chains. So in that case, we have to set the number of chains equals to 2, and then we can run these and then use the DIC.samples function to get the DIC values. Because it has 2 chains, it may just take a little longer than if we have 1 chain. And also, like I said, DIC is based on the conditional likelihood. Okay, so it actually takes 16 seconds instead of just 3 seconds. Okay, and then we can get the penalized DIC values equals this. That's the DIC from JAX. Okay. All right, that's for the linear growth curve model. And for the quadratic growth curve models, it's actually just the same. The only difference is that now this mean of y has a quadratic term like this. And now we have more parameters. So we have B of Q, also the quadratic term coefficients here. And then of course we have to set priors for that. And the models just have more parameters, okay? So we can run this quadratic growth curve models. And by when setting the initial values, then we again have more parameters, BL, BS, BQ. That's the average value for the intercept or the linear term, quadratic term, and well, yeah. And then we have the covariance matrix, inverse of the covariance matrix set like this. And again, remember to set the random number generator and set the seed. Okay. And then we can run this again. All right. 6.6 seconds, a bit longer. And again, we save the samples as a MCMC object. And then get the model estimation results. Okay, so we have all these estimation results. Interesting, it actually skipped a line here. So we can run this line to get all the parameter estimates. And then remember to conduct the convergence test. Actually, for the quadratic model, some parameters didn't quite converge, like this covariance between the intercept and quadratic term, and also the variance of the quadratic term. Well, this is the variance of the linear term. Their Guec test statistical values are above 1. Well, that out of the range from negative 1.96 to positive 1.96, indicating that they didn't converge. So when they didn't converge, what do? We can actually increase the number of iterations. So we set the burning period a bit longer and burn that, and also set this number of iterations longer to a larger number. That will definitely help with the convergence, especially for this case, it's so close to 1.96. Okay. And we can also calculate the DIC values, which also takes longer. So I'm going to skip that, but you can run that at your end. And then for the latent basis growth curve models, again, it's pretty much the same thing. The only difference from the linear model is instead of having the time t here, we have this a of t, and this a of t, we set the a1 to be 0, a4 to be 1. So the first loading and the last loading to be fixed, and the middle ones are freely estimated. Those parameters can be estimated. And for a linear growth curve model, if it's a linear, then the basis should be like 0, 0.33, 0.66, and 1, right? So it's equally spaced. But if the estimated latent bases are not 0.33 or 0.66, it means that they are not equally spaced, or they are just not linearly increasing or decreasing, linearly changed. We can run this, and when we set the initial values for this A vector, because the first number and the last number is fixed, so we don't really need to specify initial values for them. So we just set NAs, and we put the middle ones, just starting values as the linear, the values for the linear growth curves. Okay, we prepare the initial values and our data, and then we run our model. We update our model for 8,000 iterations, just use as a burning. We throw them away, and then we run another 8,000 iterations, and to get those parameters. So it takes 5.4 seconds. Now we save the samples into a MCMC object, and we can plot it. Okay, so as you probably can see here, mostly converged, but we can just check all these. All right, and we can run the Guec statistic first. See all the model parameters converged. Okay, and then we just get the parameter estimates and the HPD credible intervals. So, okay. So for the parameter estimates, this A2 latent bases were estimated as 0.49 and 0.75. That just indicate that the change is not linear, because if it's linear, it's supposed to be 0.33 and 0.66. Okay. And the average initial value is 4.9 for the math average scores, and the total change over time, average total change over time is 1.04. Okay, so we also get the variance and covariances estimate, right? And here I actually plot this. If it's a linear, then we have this from 7th grade to the 10th grade, we have 0.33, 0.666, 1. But actually here we have the estimate value is about 0.5 and then 0.75. So it actually increased faster than a linear change at the beginning and then getting slower. Okay, and the following the same procedure, we can calculate DIC, but I'm going to skip that because you can just run the code by yourself. All right, and then the next thing is to run the R code part 1 GCM missing data analysis NAR. So it's for the missing not at random data. I'm going to close this since we already run that. Okay, so it's just the same data. We can run this again. So if you already have the data, so you don't even need to do anything with it. But if you want to start over again, that's fine. Now we replace here, we actually need to create a missing data indicator. Okay, because in the model part, we have to model this missing data indicator. The missing data indicator have the same dimension as your data. So our data have 434 rows and 4 columns. So now I'm creating a missing data indicator M as a matrix with 434 rows and 4 columns. And then I just, again, replace all the 99s by NAs. But in addition to that, I create those missing data indicators. When the data are missing, when it's equals 99, then the missing data indicator is 1. Otherwise, the indicator takes a value of 0. All right. And then in JAX, in addition to what we had earlier, we also need to model this missing data indicator. Well, we're also missing to auto the missing data. Okay, so we have the add-on structure here just to model the missingness. Okay, because other than that, this part will be the same as the linear growth curve model, but we just have this additional 2 lines here. Okay, in this case, we actually have all the missing data indicators, MIT here. Well, it's actually from 2 to 4 just because there's no missing value in the first column at time point 1, right? So we allow this missing data indicator to follow a Bernoulli distribution. And this Bernoulli distribution with a parameter of missing probabilities IT, okay? And then this is just a probability, so it's from 0 to 1, and we want to interpret this probability, and we use a logic link function for this probability. So the logic link function on this missing data probability can be modeled using these. So this is actually just the missingness is predicted by the previous time points value and the current or the missing value itself. Okay. In practice, if you have additional auxiliary variables or other available informations, instrument variables, you can put those variables in here to interpret the missing values. Okay, now since we have these equations here, we have C0, C1, C2 are 3 additional parameters that are related to the missingness. So we have to specify the priors for them. And of course, we have to specify initial values for them as well. Okay, and then we can run this model and also the initial values data, and we can directly run this JAX model. We update the model for 8,000 times. Okay. So basically 8,000 iterations already burned, and then we keep another 8,000 iterations for our empirical posterior distributions. All right, and save that into MCMC. Okay, and then that's just the history plot of the parameters. Seems like the C's didn't converge, but we can just check the convergence. Okay, so the C's, the parameters that are related to the missingness didn't converge, right? And some other parameter didn't converge. So I'm really not going to show you the results, but results can just be obtained by using the summary function, and HPD equilibrium interval can be obtained. But the reason why it didn't converge is because the number of iterations is not enough. So you just need to increase the number of iterations and you will get a converged results, okay? But because of time, I'm not going to make it too long. Okay, then the next thing is to conduct a robust analysis using t-distributions. I just gave you a quick illustration of that. Okay, so yeah, this is just another data set, and we have the data read into R. Now this data set have 512 subjects with 4 variables. This one doesn't really have missing data in it, okay? And we can draw a trajectory plot and get the overall change. Okay, so when we fit the traditional growth curve model, it's just the same as what we did previously. So this is the random intercept slope follow a multivariate normal distribution, and that's why the observed score follow a normal distribution, okay? So we can have that. We actually already ran that, so I'm going to skip this, but basically these are the code we did just for the linear growth curve model. They're exactly the same, okay? But for the robust version of it, if the data are not normally distributed, actually the data are not normally distributed, so we can fit a robust growth curve model based on student t distributions. And there are different versions of growth curve model based on student t distributions, because we know that the random intercept slope follow a multivariate normal distribution, and this is why the observed score also follow multi-normal follow normal distribution. So the t distribution can really be used for either of them or both of them. So we actually have a TN model where the t distribution is used for y. We also have an NT model where the t distribution is used for the random intercept and slope. And we also have a TT model where the normal distributions for both the random intercept and slope and the outcome variables are replaced by t distributions, okay? So we can just do that by replacing this d of d norm by dt, but in that way we need to have this degree freedoms set here, and because this is the one additional parameter, so the degree of freedom need to be specified with a prior, and we use a uniform distribution from 0 to 100, which is like more like non-informative priors for this degree of freedom. Okay, so this is the TN model. Okay, and then we have the initial value specified for it. So notice that because we have one additional parameter D, so then this degree freedoms also need an initial value. And we prepare our data, run JAGs, okay, and we update our model for 5,000 times. I'm using 5,000 just because it takes longer than if we just use a normal distribution. And when the model is getting more complex, it could take even longer, okay? So that's just the update of a model. Then we need to save the CODA samples. Now we're monitoring all the parameters. Now here you can see I actually organized that into parameter 1, 2, 3, 4, 5, 6, 7. So here instead of setting like BL1, BS1 or whatever, then I'm only just putting that parameter here. So that actually saves some effort. But once we have the model, let's save that into MCMC object, and we get the GUX statistics or all the other summer statistics, we see that it's actually not going to show which values for which parameter, right? So this one actually all converged. I'm going to run all this together. So instead we're actually having these parameters here. So in that case, we have to go back to our model and figure out, okay, parameter 1 is for the intercept. Parameter 2 is for the slope. Parameter 3 is the variance of intercept. Parameter 4 is variance of the slope, and 5 is covariance between intercept and slope, and 6 is the variance of the Merriman errors, and 7 is a degree freedom. Okay, so the degree freedom is 4.2, indicating that those Y truly follow a T distribution, because if it doesn't, it follow a normal distribution, the degree of freedom, it would be really large, because as the degree of freedom goes to infinity, the T distribution would approach to a normal distribution. Okay, so we can follow the same way to calculate the DICs, but notice that we need 2 chains and it takes longer to calculate DICs. Here I actually recorded, with my older laptop, it took 497 seconds, which is 8 minutes, over 8 minutes. That's a relatively long time, right? So that's just for the TN model. The NT model is like we can just replace the multivariate the multivariate normal distribution by this multivariate T distribution. I think this should be multivariate T distribution. Okay, I'm going to definitely change that and upload that to the course website. Okay. Okay, I guess it's just copy the wrong thing. Yeah, you can see it actually takes this long to get 70% of the iterations run. And when we get to the gross mixture model, you'll see, oh, it takes so long, but sometimes it just, Bayesian could take a long time to get converge. But luckily now we have powerful computing resources. So we can do parallel computing. So usually in my lab, we're running Bayesian analysis. The time is no longer a problem. We can run many jobs at the same time with the high performance clusters. Okay, so with my current laptop, it took much shorter time, only 3 minutes in terms of 8 minutes. Yeah, I just have a new laptop, so that's good. All right, so I guess I'm just show you the TN model where the Y follow a T distribution. Okay, so let's follow a T distribution. All right, and next thing, we get to part 2. For part 2, we actually have 3 code, so we can run this because it's simulated data. So everything from the beginning to here are just used to simulate our data. So if you're interested, you can see how data are simulated. Basically, we have 3 time points, and the sample size for each group, each latent class is 200, and we have 2 latent classes. So the total sample size is 400. Well, basically, it's just a simple, relatively simple analysis or a simple data set. So we can run that. That will just simulate the data. All these 2 packages are also used for data simulation. Okay, so it's not related to anything about the analysis. And in the analysis, we'll just use our RJAX package. Okay, for the one class analysis, we specify our model first. The only difference from previous code is like we have these additional lines by specifying the log likelihood function. And we can run this. All right. And then we can load our data. In this case, we have our data like y equals 1, time is 3, and n is 400. Okay, you can actually type it. Data list. Oh, I missed the A here. Okay, so that's our data, and also time point is 3 and is 400. And we can specify our starting values, and I just gave you more options here. So in this previously in the growth curve model, we use 1 chain, and here I just have 2 chains, and then we can specify 2 set of initial values. Okay, and then we put our parameters and all these values preset. And then we compile our model by putting the model data, initial values, and number of chains equals to 2 together. Okay, and we update our model for 5,000 times. That's the burn-in period. Because it's a 1 class model, it's just a growth curve model. It didn't take long to run that. And then we save the samples from the posterior distributions using the CODA samples, again, the same function as before. And for checking the convergence, previously I gave you the code for using the GILAC test, but here, since we have 2 chains, we can use Gilman's test. So for check the convergence, we are going to use the Gilman's diagnostics. Okay. But then from that, we need to save the CODA samples as a Markov chain and name that. And we also need to select the likelihood values. So save the log likelihood values for the future use in the Lua package. And then we select model parameter values and save that to the coefficient 1. So we basically just separate the log likelihood and the coefficients, because in the MCMC chain, it actually include all the log likelihood values and coefficients, and log likelihood value is a long list. It includes a lot. Okay, so we can use the CODA package. Wait, it actually already have the CODA package because JAX automatically load the CODA package. So this is not necessary. Okay, and then we have the Gell-Mann's statistics for all the parameters. Okay, as we know, like when Gell-Mann statistics is less than 1.1, you already consider the model converged. Once the model get converged, we can summarize the posterior distributions. So we can again use the summary function, but now we have to just do it for all the coefficients, because if you just do model res or just do that, then it actually gives you all the log likelihood values. So the log likelihood takes 1,200 columns because we have 3 time points and 400 subjects, so that it actually is 1,200 or 1,200 columns. And then from after that, it's going to be our parameters. You can actually check this, but it just takes long to see that. So for example, if you do like model or res, first, so you'll see that okay, or we can do like head model or res. Oh yeah, that's probably easier to see. It's like all these, the first 6 rows were reported and the last 6 were model parameter, and before that are all the log likelihood values. Okay, so we're going to get a summary for the last 6 columns, and that gives us all the parameter values and the quantiles, and also the HPD credible intervals. If you're interested in getting the posterior mode, here's a function that you can get the posterior mode. And in fact, with the MCMC chain, you can actually get the mean, median, mode, standard deviation quantiles for the chains, and that will be the same as you would have just by using the summary function. Okay, and finally, we get the WAIC values by using the LOO package. Yeah, it's just an easy one. We get the WAIC values here. Okay. All right. So one last thing is the 2-class model with constraints. Again, the first part is for data simulation. Well, if you already run for the 1-class model, it's the same thing, okay? And here you can either use require or library. It's the same thing. Like if I'm doing this library, it will be the same. So I will load the package, and the model, as I already explained in part 2, so we have this membership indicator as a multinomial distribution. Yeah, and we also have this log likelihood value specified here. Okay, so we can run these, and we load our data, we specify initial values, and then we update our model. Okay. It's not too bad. It's slow, but not too bad. Okay. And after that, we still need to run this CODA samples. and then summarize the results and get the WASD values like this. So all these code are ready to run. You can definitely run it after workshop, and yeah, I welcome any kind of questions. Okay. Yeah, this is probably a good time to have some water. Yeah, so this is already the model. We constrain the variances to be equal. Without the constraint, it could take much longer. Okay. Okay, so that's done, and we can check the convergence. Okay, so see, like all the Gilman's statistics are below 1.1, so the model converged. And then we can get the summary posterior distributions. So this code actually written by Han. You can actually directly use the summary function we had, where she actually wrote all these by herself. That's also doable. So that's just can be summarized like what we already have for previous ones. So we got the mean of the posterior, median of posterior, mode of the posterior, standard deviation of the posterior, and equal tail credible intervals and HPD credible intervals, okay, for all the model parameters. And finally, we can get the WASD values. Okay, so I think that's everything we have. Of course, like I showed you earlier, we also have code for 2 classes without constraint, but it just takes a long time to run, and also provide the code for growth curve model with a proportion outcomes. Yeah, so that's just on the website. It's a complicated study because it actually includes a lot of things that need to be considered, and it's a more complex model than just a growth curve model. But if you're interested, definitely read that paper, and you can directly run that code or adapt that code to whatever analysis you would like to run in the future. All right, so that's my workshop for today. Again, my name is Cynthia. If you have any question, you have my contact information. Feel free to reach out. Yeah, okay, thank you, bye.